already talked about some of that. I talked about that on Wednesday, but I'll kind of go over this again. So here's our standard paradigm. We're going to design these state machines, whatever is in this green box. It's going to have some number of inputs and some number of outputs. The ones that we've already done involved problems. The sequential counter, for instance, or the non-sequential counters. There were really no real inputs. We had a clock, but we didn't have any inputs, and we also had no real outputs, other than just the state of the flip-flops. We saw, though, at the end of the chapter that we would get into trouble if we tried to do a problem where we had a repeated state, because then we couldn't really do that problem. We would have to have modified our approach. And in fact, the modification would have required us to develop an output network that would, there were two states where the output was, where all the flip-flops were 1, or F if you want, because it was a four flip-flop problem. And we had, I think, 6 states. And so F showed up in state maybe S2 and also maybe in S5. Well, all we had to do was build an output matrix that gave us our desired output for each state. And there's no reason why we couldn't have an output matrix that would give us F for state 2 and also F for state 5. But still, we would still code in our flip-flops a different state number for those 2 states. One would be state 2 and one would be state 5, even though they had the same output. And of course, we can always have the same output if we have an output matrix. So we would have to modify the problem to include an output. And in fact, when we have some number of inputs and some number of outputs with our state machine, we have our general state machine. And that really can implement almost, there's a very, very almost infinite list of problems, or maybe it is infinite list of problems we can do with that paradigm. Okay, learning objectives for this chapter. So we want to be able to design a simple state machine with up to 8 states, 2 inputs, 2 outputs. Be able to explain the difference between a sequential design with mealy outputs and another with more outputs. And be able to state when to read the more machine outputs and when to read the mealy. Now, I did already cover this in class, but I'm going to try and review this in the video to make this video more generally applicable. But the real focus of this video is going to be the traffic light problem. If you think about what is the ultimate example of a state machine, a traffic light is the ultimate example. Every one of us spends a fair amount of our life staring at traffic lights, waiting for them to change. Most engineers, actually, if they travel the same route frequently, get very good at figuring out what those traffic lights actually do. And so it's really interesting. And when they don't behave like we would expect them to, we suspect that they needed to hire a slightly better traffic engineer or something. All right, here's our glossary. We're going to talk about mealy machines and more machines. We define them here, but I'm going to talk about that separately. And then we have our state machine inputs and our state machine outputs, and those are just definitions. All right, so here's an example. This is an example of a state machine that has outputs, the traffic lights, and a whole bunch of states. But unless we have lane detectors, there may not be any actual inputs to this. And so we're gonna work on that. And the way we'll do this, we're gonna set this up with a clock that so every state takes exactly 5 seconds. And so if we want to have a condition that's going to last for 10 seconds, we just have to replicate the state and give it a new number. And so, say for instance, we would call this state S0. So we just copy state S0 to state S1, and now we have state S0 and S1 are the same thing, and that gives us this picture for 10 seconds. And if we need 15, we add another state that's identical. And that way we can build this up in blocks of 5 seconds, and we can pretty much configure this to give however many seconds we want for the east-west traffic while the north-south is stopped. And then we'll transition over to the north-south, and we'll have so many seconds for them. And we can have that separate just by adding or subtracting similar states. in this case, we've said the yellow condition for north-south could be repeated once to give 10 seconds of yellow. And then the green for east-west could be repeated 6 times to give 30 seconds of green for east-west. And then 2 times of yellow for east-west, giving 10 seconds of yellow. And then 10 repeats to give 50 seconds of green travel for north-south. Well, the idea there would be that north-south would be the main route. And then you'd have a total of 20 states, numbered 0 to 19 for this design. But there wouldn't be any input. And here's our little pictorial. And then we go to figure 12-2 and look at the state graph. Now, what I want you to see here, notice we'll show in our state graph what our outputs are. And these outputs are going to be associated with our states. But since there aren't any inputs, then the only thing we do, we always go from S0, we're always going to go to S1. There's only one path out of each one of our nodes. In fact, let me set that up just a little bit here. Let's see. Okay, so we'll transition over here. Let me write on this. And what I want to show you here is, we'll have, I've said this before, but I really want to make this point. So if we have n inputs, then we have to have 2 to the n paths out of each node in our state graph. All right. So if we have no inputs, n equals 0, so we have 2 to the 0 or one path out. If we have one input, then we have 2 to the 1 or 2 paths out of each node. And if n equals 2, then 2 to the 2 equals 4, so we have to have 4 paths out of each node. So you can see, as our inputs increase, the number of paths possible paths out of each node that we have to account for goes up by powers of 2. But with no inputs, we still have to account for one path out of each node. All right. All right, so back to our state graph. And you can see here then, right now, it starts off, it's yellow for the, let's see. So the vertical one will be our north-south. No, maybe the horizontal one will be our north-south. So it starts east-west, right? Yeah, okay. So we start with yellow for east-west and red for north-south. 5 seconds, 10 seconds of yellow, and now it's green for north-south and red for east-west. And it's green for north-south and red for east-west for 5 seconds, 10, 15, 20, 25, 30. Then it's yellow for 10 seconds, 5, 10. And then it's green for north-south. Did I do that right? Let's see. Yeah, I think I did. So now it's green for north-south. 5. Yeah, hang on. No, I said this is east-west. I think I did this wrong. Well, okay. I wish I had labeled these because it is a little confusing to me. So this is yellow for north-south, green for east-west for 30 seconds, yellow for east-west, green for north-south for 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, and then back up here, yellow for north-south, and then green for east-west, yellow for east-west, green for north-south, and so forth. And we just go around and round. But you notice this one doesn't have any input, so we only have one possible path out of each node. All right, so let's complicate it a little bit. And this whole thing takes about 100 seconds for the complete, for all the states. All right. Now we're going to add a little lane sensor here for a left turn lane in our north-south turn. Now, I'm not going to make a big distinction about the northbound versus the southbound. you can just imagine we've also got a left turn lane over here, and we're just going to do it like this. Or maybe there's no left turn lane here, and we're just going to let this be a northbound thing. And I can't remember how I set that up exactly, but okay, so here's the state graph for that. Now, what's interesting is that, so all we've done is we've added this sensor here. So even though we have one input, we ignore the input for all the other states except when we get to S9, and then in S9 we're going to check the input. So in all these others, the input is always, it's assumed to be 0. Doesn't matter. We don't really check it till we get to the second yellow condition. So again, it's our east-west is green, and now we're ready to turn it green for north-south. But if the sensor is true, and that's what the X stands for here, that means yes, there is a car in the left turn lane. Then we're going to go down here. But if there's no car in the left turn lane, then we're just going to make it green for north-south. Here, we're going to make it green for north-south going northbound with a left turn arrow as well, and we'll leave it red for the other northbound group, for the southbound traffic, and also for the east-west traffic. And then once we do 5 seconds, 10 seconds of left turn, then, and we'll call those states 9A and 9B, then we'll go to 10. Again, the only node that actually has to have 2 paths out is S9. And so in S9, we're gonna check this sensor, and we're gonna take this path. Once we get back to S10, we just continue on around with 30 seconds of green for the northbound, and then now we're back to the yellow condition for northbound and repeating the process. All right, so that shows how we can have that sensor and include one input. And where we do consider the one input, then we do have 2 paths out. In all these other places, we're basically ignoring the sensor, and we're making both paths, regardless of what the sensor indicates, both paths are going to S1. And both paths will go to S2 and so forth. So the sensor's just ignored by virtue of making both paths go to the same place. But here, we separate them out. Okay. How do we proceed from here? Well, okay, so now we've got 20 states plus 2 more, so we've got 22 states. So here's what we'll do. And we'll label them S0 to S19, but we'll throw in a 9B, 9A, and a 9B. Okay? So if we're in state S0, then regardless of the sensor reading, we're going to go to S1. And in S1, we're going to, regardless of the sensor reading. So we're going to ignore the sensor reading until we get to S9. In S9, if the sensor shows no cars, we'll go to S10. But if it shows a car, we'll go to 9A. And then in 9A, we'll always go to 9B, regardless of the sensor. And in 9B, we'll always go to S10. Then in S10, always go to 11, 11 to 12, and so forth, completing the rest of the chart. And 19, we'll go back to S0. And here's how we're going to do the lights. So we have now the one thing we're going to have to break out. We have to break out the east-west green can be the same, and the east-west red can be the same, and the east-west yellow can be the same. But for the south, we have to separate the south red, the southbound red, from the northbound red, because normally they'll be doing the same thing, except when we get to 9A. And here we're going to leave this northbound, the southbound red is going to continue to be on until the left turn finishes, if we do the left turn. If we just go to 10, then we'll skip that. And then we'll make both the southbound green and the northbound green, and the left turn arrow will be red. Again, anywhere there's not a 1, we assume that the light is off. So the light's only on when the output's 1. Otherwise, we assume it off. And then that'll continue for 30 seconds of green, and then we'll go back to S0 and show yellow for both north and south directions. Okay. And we didn't include a yellow error, and you don't always get yellow arrows. Sometimes it just the green arrow goes off, and then the northbound and southbound green, or the southbound green, just comes on. Okay, I guess strictly speaking, you probably should have a yellow arrow, but we didn't put one in. Okay, so that's how the problem looks in a truth table, and then of course, so all we have to do now is basically write these equations out and simplify them. In this case, we have a lot of states, so we have more variables than we can use with K-maps. So we'll have to use other techniques like computer-based tools, or we can actually just use switching algebra and simplify it that way as well. We can just write out our minterms. Okay. So we only have 20 states. So we actually, how many flip-flops do we need to cover 19 states? Well, the nearest power of 2 would be 32. And so that's 5 flip-flops. So we can cover this with 5 flip-flops. We'll have a bunch of don't cares. We could use a 6-variable K-map with our lane sensor as one variable and then our 5 flip-flop inputs as the other 5 to make 6. That'd be a little tricky. It's not that, it wouldn't be that tough because there's only one place where we have to really consider that 6th variable. So we can probably make that work. But an easier way to do that is with a state machine chart, and we're going to cover those in just a few chapters. All right. Now the other thing that we did in this, in this chapter, we're going to give a simple design where we can easily solve it with some 3-variable K-maps, and that'll be a lot easier to work with. Not quite as many outputs, not quite as complicated as the traffic light. So let's look at this. So the first off, so here's our problem. We're gonna look for a code detector that reads a serial input and looks for the input code 110. All right, so this is gonna look for 110, and which is a binary 6. Okay, now we're gonna allow. We're not going to reset, but the truth is the targets can't really overlap because the last element is a 0 and it's not the first element, so basically there's no such thing as overlapping targets here. So once we finish a target, once we get a target, we're going to be starting over. All right, we're going to now, how do we know if we have an input stream? So let me write on the paper just a little bit here. Let's see, I'll transition. So let's say we have a our little network here. This is our network. So we have one input and it's X. We have one output Z. And Z is going to equal 1 when we get a sequence of 3 values that are 1, 1, 0. That's our target. Now, the way we're going to do this, let's we've got a little state graph. I'll draw it here, but then I'll pull it up on in the textbook. So we're going to start in S0, and in S0, and I think let's see how we did this. Oh yeah, we did it. Okay, I have slides. Maybe all right. The textbook kind of works through it. All right, we're gonna. So in S0 we have nothing for our target. So we don't have anything. We're looking for the first one. If we get a 0, we're going to stay here because we still have nothing. Okay? If we get a 1, we'll go to S1. And there we have the first one. But we're still going to output Z equals 0. And here Z equals 0. Now, so we're going to go here on a 1. Now, if we get another 1, now we're going to go down to S2, and now we have 2 1s. but z still equals 0. And then if we get a 0, now we have a target. We'll go to S3. We have a target of 1, 1, 0, and the z will be equal to 1. Now normally, we don't write z equals to 1. We just put z there, and we don't write z equal to 0. We just leave it out. So if you don't see z, then you know that it's 0. So we could redraw this. Let me just redraw this, make it a little neater. So we'll do S0, and that'll be nothing. We'll stay here on a 0, and on a 1, we'll go to S1. Now we have a 1. Z is still 0, and we're just not going to say anything about it. And then we're going to go to S2 on another 1. And now we have 2 1s, but we still don't have a target, so Z would still be 0. And then finally, we get a 0, and now we're in S3. We have a target, 1, 1, 0, and we have Z equals to 1. Now here, if we get a 1, we can go here on a 1, and here we go here on a 0, because we still don't have anything. What happens if we get in S2 and we get another 1 instead of a 0? Well, we can just stay here because we still have 2 1s. So on a 1, we'll stay here. What happens in S1 if we get a 0? It means we don't have anything. We have to go back here. So that's what that looks like. Okay? Notice now we have 2 paths out of every node. Out of S0, we've got a path for 0 and 1. Out of S1, we have a path for 0 and 1. Out of S2, we have a path for 0 and 1. And out of S3, we have a path for 0 and 1. Notice how the only place Z shows up is here, because that's the only place Z is 1. And everywhere else, we just leave it out, and that means that it's 0. Okay? All right, now we'll go through the book. Same kind of thing here. Let me transition. Okay, so we start in S0, nothing. And I'll put X prime here, which means our input is 0. And I'll put X here. Now the truth is, I can delete these. I don't really need the X prime. I'll just leave this off, and I'll only put the X on this one. So if our input is 1, we're going to S1. Otherwise, we're staying here. And then if we get a 0 here, we're going back. But if we get a 1, we're going to S2. And now we have the second one. And then if we get another 1, we're staying here. But if we get the 0, we're going to S3, where we have a target, Z equals 1. And then we're going to add in the other paths where we stay here on a 1, and here we go back to here on a 1, and we go back to 0, S0 on a 0. And so now we have 1, 2 paths out of S0, 1, 2 paths out of S1, 1, 2 paths out of S2, and 1, 2 paths out of S3. And now we'll clean it up by taking off all of the X primes. So if you don't see any marking on the link, you know that the inputs are 0. So here the inputs are 1, we go to S1. Here we get another 1, we go to S2. Here we get a 1, we stay in S2, but obviously on a 0 we go to S3. On a 1 we go back to S1, and on a 0 we go to S0. And the only place we show Z is here, and we don't say Z equals 1. Just by the appearance of Z, we know that it's a 1. So that cleans up our notation a little bit and makes it easier to read and kind of declutters all this. I don't really care whether you write in X equals 0 and X equals 1, or you put in zeros or ones like I did on the paper, or whether you do it like this. It really doesn't matter. You can do it however you want. All right. So here's how this flow occurs. Okay, we do a state graph, which is a graphical depiction of how the inputs drive the next states and the outputs. Okay, and the whole idea is to capture the design with our state graph and to think our way through it. Then we have a state table where it's essentially the same information. It's just in tabular form, and we use that to review. And also, it's a good way to look at how we might reduce the number of states, and we're going to talk about this in an upcoming chapter. Then we determine how many states we have after we've reduced the state table, if possible, and we figure out how many flip-flops it's going to take to encode all our states. Then we come up with a proper flip-flop state encoding, and then we assign our flip-flop states. And when we substitute in the flip-flop encoding for each of our states, then that gives us a transition table. In this case, we have 4 states, S0, 1, 2, and 3. So we need 2 flip-flops. And we can just do straight binary encoding. So S0 could be A is 0, B is 0 for the flip-flops. S1 could be A is 0, B is 1. S2 could be A is 1, B is 0. And S3 could be A is 1, B is 1. And that would encode all 4 states in straight binary order. It turns out whenever we have 3 or 4 states, that's kind of a special case. And we actually can, there's some things that we can think about with respect to that. It turns out that how you encode your states can in fact change how much hardware it takes to implement the problem. So sometimes what we'll do is we'll think about this, and so here's how this works out. Smarter people than me have kind of thought this through, and here's what they've concluded. All right, let me transition. Okay, so for 3 or 4 states, there are only 3 non-equivalent ways you can assign states. Now we're going to look at this in a later chapter in a little more detail, but I just want to touch on it here. And it turns out those 3 non-equivalent ways are, you can assign it. So here, straight binary would be, here's our states, S0, S1, S2, and S3. And our flip-flops for A and B, we can assign it, A and B are 0, 1, 2, 3, straight binary. We can do A and B are 0, 1, 3, 2, and we can do 0, 3, 1, 2, where our third one kind of moves up in the ranks, and we always start with 0. Those 3 different assignment strategies cover all the possible ways. You can actually do it 24 different ways, but of those, there are only 3 non-equivalent ways to do it. So all 24 ways break into 6 doing it one way, where you have the same amount of hardware, it's just moved around from flip-flop to output or whatever. And then another 6 where it's moved around a little bit, but it's the same amount of hardware. And finally another way. And it turns out that it's not unusual at all that there is actually one of the ways may be significantly less hardware. Now, it's not guaranteed, but it often turns out to be the case. And so for some things where you really want to squeeze every gate out of your design, you may want to spend the time trying to do this. But once you get past 3 or 4 states, the number of non-equivalent ways to assign them is so large that you generally can't look at it. You can't brute force it and look at all possibilities. But with 3 or 4 states, you can. So I just want to make that point. We'll come back to that in a later chapter. Okay, so what we're going to do now is we're just going to advance to the transition table, and here it is. We have our states encoded with flip-flop A and B, 0, 0, 0, 1, 1, 0, and 1, 1 in binary order. Here's the next states, straight off of our state table, just with our encoding substituted. And here's our output for Z. And now these turn into K-maps. The A columns are taken off, and we do X at the top, AB down the side, and we have K-maps for our D sub A input, our D sub B input, and because we don't have X is not involved in the output Z because it's a Moore machine, then we just have a 2-variable map, and there's our output, and that would be AB. Okay, And so this is going to be that's going to be x a prime b, and this is going to be a b prime. So that'll be a 3-variable term, a 2-variable term, and then here we have three 3-variable terms: x a prime b prime, x a b, and x prime a b prime. And so then we draw the circuit, and I don't think I put that on there. All right, so that's that problem. Okay, what I want to do now, I just want to kind of review what I've said about the Mealy and Moore, and then I want to go through one more simple problem, and we'll try and we'll try and repeat what we just did. Only I'm going to do it. I'm going to do it first with a Mealy machine, and then I'll do it with a Moore machine. Or maybe I'll switch that around. I'll do it with the Moore machine first, and then I'll do it with a Mealy. But it'll be a similar problem to what we just did. It's just that we're going to have a different target. Okay. All right. So let's do that. And for this, I'm going to use slides. Okay. So a Mealy and Moore machine. So what I want you to see here is that we have in the Moore machine, the output is a function of the present state only. And it doesn't change when the new inputs come in. It only changes when the clock edge hits and updates the flip-flops to the next state. So in our present state, as long as we're in our present state and we don't change to the next state, our outputs are the same. Whereas in a Mealy, the output function requires the present state plus the new inputs before we update to the next state. So the Mealy machine is looking forward to the next state, and the Moore machine, not to the next state, but it's looking forward to the new inputs. Whereas the Moore is just locked with the present state. Okay. So in a Mealy machine, the inputs usually show up as variables in our output function. In a Moore, they can never be in the output function directly because it only depends on the state. So we only have to know the settings on our flip-flops to calculate our outputs. Okay, and if in fact in a Mealy machine, if we have outputs that don't depend on the new inputs, then they're not Mealy outputs. They're really Moore outputs. All right. So we're going to do a new problem here. Again, a sequence detector. This time, we're going to use a target of 1, 0, 1. Now, in this case, we're going to allow overlapping targets. We're going to let that last one be the first one in a possible new target of 1, 0, 1. Otherwise, it's exactly the same. We're going to use a Mealy network initially, and then we'll do it with a Moore. We have to figure out how many flip-flops, but we're going to have 4 states, or 3 states with a Mealy and 4 states with a Moore, so we're going to need 2 flip-flops both times. But you wouldn't know that at the beginning. You have to do the state graph and figure that out. And we're not going to reset after we detect. We're going to allow for overlapping targets. Okay, so let's do the state graph. Now, normally the way you should approach these problems is write out your block diagram. You have an input X, you have an output Z, you have a clock, and you have the network you're going to design inside the box. And then often we should construct a typical sequence. Here's our input X, and again, remember, our X input is synchronized by the clock. So our network in here knows when to read the next X because that X has to be synchronized with the clock. Otherwise, we would have no idea when to read it. And so that's just a requirement. And that's why these sequential circuits almost always have clocks, because although in theory you could do it without a clock, how would you be certain that the X would be arriving at the right time? And the answer is it would take a lot of coordination with our upstream logic and with our downstream logic not to have things just get completely out of control. All right, so here's our sequence. We first get an X is 0, output is 0. We get an X is 0, output is 0. We get an X is 1. That could be our first item in our next sequence. Output is 0. Oh, but we get a second one. Okay, so now that could be the first in our target sequence. Output is 0. Now we get a 0. Okay, we're working on our target. We've got the first 2 items, but we still output a 0. And boom, we get 1, 0, 1. There's our target. We output a z equals 1. Now we get another 1, so that's not a target. That's 1, 1. So we make that a 0. Now we get a 0, still not a target, another 0. And then we get a 1, still no target, a 0. Then we get a target, boom. So that's our first one. Then we get a 0, which could be the second item in our new target, with this 1 being the first one in the next target. And then we do get a 1, so boom, we get 1, 0, and then 1, another target. All right, so that's our test sequence. So we kind of helps us understand that we know for sure how this thing is supposed to work. Okay, now we're going to do the state graph. Now, because our outputs are associated with our links, we're gonna have two numbers on each of our connections. Now you saw in the book I used x for the input, and x if it was 1, and x prime if it were 0, and then in our final state graph we cleaned it all up and got rid of all the x primes and just left those blank. So you knew if there was no input on the link, that meant x was 0. I'm gonna use numbers, and I don't care which you do. I think you'll see as time goes on, a more sophisticated way to do it is to use the variables and not the numbers. But and that way you know the prime is a 0 and so forth. Okay, so here we go. So we're going to start with S0, and notice here we don't have any output associated directly with the state because this is a mealy. So if we get a 0, we're going to stay here, and we're going to, the red is our x and the blue is our z, and we're going to output 0. Then if we get a 1, we're still outputting 0, but we're going to go to S1. And that tells us we have the first item in our 1, 0, 1 sequence. Then if we get another 0, we're going to go to S2. Now we have the second item, still outputting a 0 though, the blue. Then in S1, if we get another 1, we can't go on to S2, but we can stay at S1, and we output a 0. So our x is 1, but our output's a 0. In S2, if we get a 0, we're going to be thrown back. No, sorry, I spoke out of school here. If we get a 1, that's a target. And we're going to go back to S1 because it means we have the first one in the next possible sequence, plus our output z is a 1, which means we just got a target. But in S2, if we get a 0, now we're in trouble. We don't have anything, so we're going back to S0 and outputting a 0. Okay, so now we have a completed state graph. We have one input, so how many paths out of each node do we have to account for? 2. All right, so we have 2 paths out of S0, we have 2 paths out of S1, and we have 2 paths out of S2. So that's a completed state graph. We now map this to a state table, just 3 states, 0, 1, and 2. We will have a don't care state. So if we code this in straight binary, AB 0, 0, 0, 1, 1, 0, and 0, 0, we'll have a don't care state. And then here's our completed. Notice now we have 2 columns for our output. 1 for x equals 0 and 1 for x equals 1. And that's because our output is a mealy output. So we not only have to be in a certain state, but we have to wait for the next input to know what the correct output would be. Now in this state, it didn't matter. We're outputting 0 either way. But in this state, if we output it before we get their next input, and the input happened to be a 1, we'd be outputting a 0, and it'd be the wrong thing. All right. Now we substitute in, for these states, the AB designations. 0, 0 for S0, 0, 1 for S1, 1, 0 for S2, and we have a don't care, 1, 1. Now we take this column and this column for the A input, this column and this column for the B input, and these 2 columns for the Z output. And that gives us 3 K maps, here, here, and here. Notice, we group these, we get our DA input, our A plus, our next state for the A flip-flop would be A prime, X prime B. For the B, it's just X, and for the Z, it's XA. And that's it. Notice here, unlike our mealy, unlike our Moore where we had just A and B, we had a 2-variable network. Now we have 3 because it also does depend on X. And notice there is an X in this equation, in this network. All right, and there's our hardware. All right, let's do the same problem now using more. Same thing. Now we start from S0, but we have to specify our output. Again, we could just leave this blank because we know Z would be 0 until we write a Z in. But in this case, I'm going to put the number, so I'm going to put a 0. And then if we get a 0, we're staying here because we're looking for a 1. If we get a 1, we're going to S1. Still outputting a 0. Again, notice that the outputs are not associated with the links now. They're associated with the nodes. Now, if we get a 0, we're going to S2. And if we get a 1, we can stay here because we still have that first 1. In S2, if we get a 1, if we get a 0, now we've got 1, 0, 0. That's nothing. We're going back to S0. And we'll output a 0, of course, here. But if we get a 1, now we're going to S3. Let's see. Let me back up. If we get a 1, we're going to S3. Oh, I guess it didn't put it on. Well, okay, so there's the 1. In S3, if we get a 0, we now have a 1, 0 for our next target. So we're going back to S2, looking for that final 1 to have a target. If, on the other hand, from S3, if we get a 1, then we still have our first 1 in our next target. So we're going to S1. We actually have 2 1s, but we only can use one of them. All right, now that's a completed state graph. Remember, 2 paths out of every node. S0, we have a path for 0 and 1. S1, a path for 1 and 0. S2, a path for 1 and 0. S2, a path for 0 and 1. And S3, 0 and 1. Oh, I didn't put the 1. There's the 1. 0 and 1. All right. So now we can extract that to a state table here. Notice we have just one column for our output again because it's a more. The output does not depend on the next input, just on the current state. And then, so now we're going to do, we didn't use straight binary. We got a little tricky here. For state S0, we did 0, 0. For state S1, we did 0, 1. But for state S2, we did 1, 1. And for state S3, we did 1, 0. So we kind of flipped them around here. What's kind of nice about this, when we do the transition table, because it's organized 0, 1, 3, 2, you don't have to flip the rows when you extract it to the truth table, to the K-map. You can just take 0, 1, 0, 1 and 0, 0, 1, 0 for the A, like this, 0, 1, 0, 1 and 0, 0, 1, 0. So you don't have to flip rows here because we already flipped the rows in our transition table. Now, I don't know if this is a good idea or bad idea, but anyway, you can certainly do this. Normally, I just do straight binary order, and then I always extract it exactly the same way. You have to remember you flip these in order not to mess this up and get the wrong K-map. Okay, and then again, our K-map for our output is going to be just 2 variable, and here our output is Z equals AB prime. Here we have 3 variable terms, A prime BX prime, AB prime X prime, and ABX. And here we have 3 2 variable terms, AB prime, A prime B, and A prime X. So you can see here, our output function is just Z equals AB prime. Notice there's no X involved in the output function because it's a more, only depends on the state. In this case, the state would be 1, 0, or state S3, because remember we coded that state 1, 0. We kind of were tricky. Notice we have one whole more state. We have 4 states in the more. We only have 3 in the mealy. And look at our hardware. Look at all the hardware we've got for this problem now. 2 flip-flops, but we've got a whole bunch of gates. 1, 2, 3, 4, 5, 6, 7, 8, 9 gates. A lot more gates than we had in our other one, in the more. And that's what we see. Generally, we have a lot more gates in our more solution, but we have a little simpler problem with our downstream logic, because our downstream logic just can read the output anytime shortly after the clock edge. We just have to give the circuit time to settle, and then we can read it. Whereas with the mealy, we have to wait not only till the clock hits, the circuit settles, and we're in our state, but now we have to wait till the new inputs come in, and we have to read it before the next clock edge. So again, you read this a little after the clock edge, and in the mealy we have to read it just before the next clock edge. All right. So I think that pretty well covers it. I will say I did go through the traffic light problem here, and since we've already looked at this, I'm just going to flip through this real quick. What I want to show you. So here's the traffic light, and notice we have a camera. Sorry, we have a camera to detect whether there are cars in their turn lane or not, or maybe waiting on the side road or whatever. Here we use a concrete saw and we bury inductive loops in the roadway, and then they change their resonant frequency when the metal's over the top of them, and that's how they sense the presence of cars. But if some doofball doesn't pull up far enough to be right over this to trigger it, or if the freeze-thaw cycles have broken the wires in here, these are hard to fix. These cameras are a lot easier to fix. I did ask a traffic engineer, if the cameras are just much cheaper, much better, and he said no, they're not, because the cameras can have problems too. If the camera is facing east-west, you can have the sun shine right into the camera and blind it, and then for a small amount of time every day it won't work. That's always a problem. They put hoods on them, but they still can't turn that off completely. And also the camera can get fooled. They can be real foggy and they can't see. They can get water and stuff up here and ice, and it can screw it up. And cameras break too. Trucks go by and hit these lights and break the cameras. But it's a little easier to replace the camera than it is an inductive loop in the road. He says they cost about the same. Turns out you have to have fairly sophisticated AI software running on these. So it's a bit of a wash, but my guess is you'll see more and more cameras and fewer inductive loops, just because this is a little more labor intensive. Okay, so here's our traffic light, just like before, and no left turn arrows, and then we have this basic thing, but then we go through all these. Now we put in the left turn thing, and now we have 20. So here's the way these are all, we have 9 lights to control, okay? Some of them we can pair up, east-west red, east-west yellow, east-west green, that's fine. South red, south green, north red, north green, north left arrow, and north-south yellow. And that's how we kind of do it. And then here's our state table with 22 states, including 9B and 9A and 9B. We have an input for our sensor, and in every case except for at 9, there's no difference between which path we take. But here we go to S10 if our sensor shows no cars, and we go to 9A if it shows a car. Everywhere else we ignore the sensor input. And then the ones, just like before, indicate the lights are on, and blank squares indicate they're off. So we need 5 flip-flops, 22 states, 9 outputs, and so we're going to do the K-maps. Here's our K-map for the east-west red. We can loop all this and do those, and then we have a few others we have to do like that. And then we can do here's for the DA flip-flop. Again, we got 4 maps here. We did this. This is it's a Moore machine. So for our output, for this output, we didn't have to worry about it. But for the DA flip-flop, we did have to consider it. And so this shows the don't cares don't depend on the X variable, just A, B, C, D, E, since they're for states 22 through 31. All right, so anyway, so this is all constant 1, and we just have to loop that 1, so that's the only real term. But what we'll see is that it's a lot easier to do this with an SM chart than it is to do it with these 6 variable K-maps. Again, we pulled out X and A, so this is X is 0 and A is 0. This is X is 0 and A is 1. This is X is 1 and A is 0, and this is X and A are both 1. And then otherwise we have B, C, D, E in our map. And then so you can see that that's just an example of how you could do the maps. Okay, I'm going to pretty much stop with that. We're at 52 minutes, so I don't want to go any longer anyway. So I've pretty well covered everything I want you to know in Chapter 12. And I'll probably do a short video Friday, tomorrow, and post that. And we will then see you in class. I'll do another video for Monday, and I'll see you in class on Wednesday. Just a few more classes to be had, actually. All right.